Welcome to Relaxing Fact Studio, a quiet space where curiosity slows down and science tells its story in a calm, thoughtful way. In today's video, we begin a fascinating journey through Earth science, traveling billions of years into the past to understand how our planet was formed and how it continues to change beneath our feet. With no rush and no noise, we'll explore the powerful natural processes that shaped the Earth, layer by layer, moment by moment through time. Settle in, take a deep breath, and let Relaxing Fact Studio guide you through the calm, remarkable story of our ever-changing planet. Around 4.6 billion years ago, long before oceans, continents, or even air existed, the story of Earth began in a quiet region of space filled with dust, gas, and slow-moving particles. This vast cloud, known as the solar nebula, was left behind by earlier generations of stars. Over time, gravity gently pulled this material together, forming the young sun at the center and a swirling disk of matter around it. Within this disk, tiny particles collided and slowly stuck together. Over millions of years, these small grains grew into larger bodies called planetesimals, some stretching hundreds of miles across. As they continued to collide and merge, heat built up inside them. One of these growing bodies would eventually become Earth. As early Earth increased in size, its internal heat rose dramatically. This heat came from constant impacts, increasing pressure, and the natural decay of radioactive elements. The planet began to differentiate, meaning heavy materials like iron sank toward the center, forming the core, while lighter materials rose upward to create the mantle and crust. This process set the foundation for everything that followed. Earth became a layered world with a solid interior, a dynamic surface, and the energy needed to drive change over immense periods of time. From this slow and orderly beginning, the planet we recognize today quietly started to take shape, one collision, one transformation, and one moment at a time. Although the ground beneath our feet feels solid and unmoving, Earth's surface is quietly in motion at every moment. This slow but powerful movement is driven by a process known as plate tectonics, one of the most important ideas in Earth science. Earth's outer shell, called the lithosphere, is not a single unbroken layer. Instead, it is divided into massive pieces known as tectonic plates. These plates float atop a warmer, softer layer of the mantle and move at roughly the same speed that human fingernails grow. While this motion is almost impossible to notice in daily life, its long-term effects are enormous. As tectonic plates move, they interact along their edges in different ways. In some regions, plates slowly pull apart, allowing molten material from below to rise and form new crust. In other places, plates collide, crumpling and thickening the crust to build vast mountain ranges over millions of years. Elsewhere, plates slide past one another, releasing built-up energy deep within the Earth. What makes plate tectonics especially remarkable is that it connects nearly every major feature on the planet's surface. Oceans open and close, continents drift across the globe, and landscapes are constantly reshaped, all through steady, natural processes operating far beyond human timescales. This system also plays a critical role in Earth's long-term stability. By recycling crust and regulating internal heat, plate tectonics helps maintain the dynamic balance that has shaped the planet for billions of years. The ground may seem still, but beneath it, Earth is always quietly on the move. Beneath the landscapes we see every day lies a hidden world of distinct layers, each playing a vital role in how Earth functions as a planet. Although humans have never traveled far below the surface, scientists have uncovered Earth's internal structure through careful observation and precise measurement. The outermost layer is the crust, a thin and fragile shell that supports continents, oceans, and all known life. Compared to the size of the planet, the crust is surprisingly shallow, yet it contains an incredible variety of rocks, minerals, and landforms shaped over vast stretches of time. Below the crust lies the mantle, a massive layer that makes up most of Earth's volume. While it remains solid, the mantle behaves slowly and plastically under intense heat and pressure. This gradual movement transfers energy upward, driving surface changes and powering the motion of tectonic plates. At the center of the planet rests the core, divided into two distinct regions. The outer core is a liquid layer rich in iron and nickel, whose movement generates Earth's magnetic field. Deeper still is the inner core, a solid sphere compressed by immense pressure and extreme heat. Together, these layers form a connected system that has been operating for billions of years. Heat flows outward, materials circulate, and energy is constantly redistributed. From the crust we walk on to the core we cannot reach, Earth's layered interior works quietly and continuously, shaping the planet's past, sustaining its present, and influencing its future in subtle but profound ways. Volcanoes are among Earth's most dramatic natural features. Yet their story begins deep below the surface, far from the erupting lava we often imagine. They are windows into the planet's inner workings, revealing the immense heat and pressure that shape our world. Volcanoes form where molten rock, called magma, rises from deep within the mantle and pushes toward the surface. This usually happens along the edges of tectonic plates, where the crust is weak or fractured. As magma ascends, it collects in chambers beneath the surface, slowly building pressure over time. When the pressure becomes too great, the magma breaks through, erupting as lava, ash, and gases. There are different types of volcanoes, each with its own unique story. Shield volcanoes grow gently with flowing lava, creating broad, sloping mountains. Stratovolcanoes build steeper peaks through alternating layers of lava and ash. And cinder cones, smaller but no less fascinating, erupt quickly, forming sharp, rocky hills. Volcanoes do more than shape landscapes. They recycle Earth's crust, bring nutrients to the surface, and even influence the atmosphere by releasing gases that interact with climate over long periods. Some of the planet's most fertile soils, home to thriving ecosystems and agriculture, owe their richness to volcanic activity. Despite their power, volcanoes are part of a slow, natural system that has operated for billions of years. They remind us that Earth is alive, constantly changing, and quietly reshaping itself, often in ways we can see, sometimes in ways we cannot. Each eruption is a glimpse into the forces that have formed our planet from the inside out. Although the ground beneath us seems steady, Earth's surface is constantly shifting, sometimes in ways we can barely detect. Earthquakes are the natural result of these subtle but powerful movements, offering a glimpse into the planet's restless interior. Earthquakes occur primarily along the boundaries of tectonic plates, where immense forces build over time. As plates press against, pull apart, or slide past each other, stress accumulates in the rocks along faults. When the stress exceeds the strength of the rocks, it is released suddenly, sending waves of energy through the earth. These waves cause the ground to shake, sometimes gently, sometimes with surprising intensity. Scientists study earthquakes using specialized instruments called seismometers, which record the vibrations traveling through the planet. These instruments help measure the magnitude and intensity of earthquakes and reveal patterns that allow researchers to understand Earth's inner structure. By analyzing seismic waves, scientists can even infer details about the mantle and core, which remain unreachable by direct exploration. Earthquakes also play an important role in shaping our planet. Over millions of years, they contribute to the formation of mountains, valleys, and other landforms. They are part of a natural system that redistributes stress within Earth's crust, helping maintain a long-term balance. Although the shaking can be startling, earthquakes are normal, ongoing process of a dynamic planet. By understanding how and why they happen, we gain insight into the immense invisible forces continuously shaping the world beneath our feet. A reminder that Earth is alive, moving, and constantly evolving.
Rocks may seem solid and unchanging, yet Earth is continuously recycling them through a slow and fascinating process known as the rock cycle. This natural system transforms rocks from one type to another over millions of years, connecting volcanoes, mountains, rivers, and oceans in a dynamic loop of change. The cycle begins with igneous rocks, formed when molten magma cools and solidifies. Some of these rocks emerge at the surface through volcanic eruptions, while others solidify deep underground, slowly crystallizing over time. Over centuries, wind, water, and ice break down these rocks into tiny particles through a process called weathering and transport them as sediments to new locations. These sediments gradually compact and cement together under pressure, forming sedimentary rocks. Layers of sandstone, limestone, and shale tell the story of ancient rivers, oceans, and deserts. They record Earth's history, preserving fossils and evidence of long-gone environments. Deep beneath the surface, heat and pressure can transform both igneous and sedimentary rocks into metamorphic rocks like marble or slate, changing their structure and appearance without melting them. Eventually, rocks may melt back into magma, completing the cycle. The rock cycle illustrates that Earth is never static. Mountains erode, rivers carry sediments, and molten rock returns to the surface in a continuous rhythm. This slow, natural recycling shapes landscapes, supports soil formation, and even affects the atmosphere over long timescales. By observing rocks, we witness a story billions of years in the making, a story of transformation, resilience, and the constant, quiet reshaping of our planet beneath our feet.
Mountains are among Earth's most majestic features, towering over landscapes as silent witnesses to the planet's long history. But their formation is a slow, powerful process that reveals the dynamic forces at work beneath our feet. Most mountains form where tectonic plates collide. When two plates push against each other, the immense pressure causes the crust to fold, crumple, and uplift. Over millions of years, these movements create towering peaks and rugged ranges. The Himalayas, for example, continue to rise as the Indian plate presses against the Eurasian plate, a process that began over 50 million years ago. Mountains can also form through volcanic activity. As magma rises from deep within the earth, it erupts onto the surface, building cones and ridges over time. These volcanic mountains are often younger and grow faster than fold mountains, shaping the landscape in dramatic and sometimes sudden ways. Another process, fault block mountain formation, occurs when large blocks of crust are pushed upward or tilted along faults. This creates sharp ridges and valleys like those found in the Sierra Nevada of California. Beyond their striking appearance, mountains play essential roles in Earth's systems. They influence climate, direct river flow, create unique ecosystems, and expose ancient rocks that reveal the planet's history. Erosion, glaciers, and weathering continuously reshape mountains, reminding us that even these seemingly permanent giants are part of a dynamic Earth. By studying mountains, we witness the incredible patience and power of natural forces, processes that take millions of years, yet leave marks so dramatic that they inspire awe, curiosity, and a deeper understanding of the ever-changing planet we call home.
Though invisible, Earth's atmosphere is one of the planet's most remarkable and essential systems, quietly supporting life and shaping our environment. This thin layer of gases surrounds the planet, protecting it from harmful radiation, regulating temperature, and circulating energy and moisture across the globe. The atmosphere is made up of multiple layers, each with its own role. Closest to the surface is the troposphere, where weather occurs and where we live and breathe. Above it, the stratosphere contains the protective ozone layer, shielding life from dangerous ultraviolet rays. Higher still, the mesosphere and thermosphere guard Earth against meteors and absorb solar radiation, while the exosphere gradually transitions into space. Earth's atmosphere is not static. Air constantly moves, driven by the sun's energy, forming winds, storms, and ocean currents. Water vapor rises, clouds form, and precipitation nourishes ecosystems. The atmosphere also distributes heat, helping maintain a climate that allows life to thrive. Over billions of years, the atmosphere has evolved. Early Earth had little oxygen, but volcanic activity, chemical reactions, and the emergence of photosynthetic organisms gradually transformed it into the life-sustaining mix we rely on today. Beyond protecting and sustaining life, the atmosphere influences nearly every natural process on Earth, from shaping landscapes through erosion to guiding weather patterns and ocean circulation. Though we cannot see it, the atmosphere is a constant, invisible companion, quietly balancing Earth's systems and enabling the diversity of life we see today. Understanding this delicate, complex layer reminds us that even what we cannot see has a profound impact on the world we call home. Water is one of Earth's most essential resources,
Yet it is never truly still. It moves continuously through the water cycle, a dynamic system that connects oceans, clouds, rivers, and the land in a seamless loop. This cycle has been operating for billions of years, sustaining life and shaping landscapes across the planet. The cycle begins with evaporation, as the sun's energy warms oceans, lakes, and rivers, transforming liquid water into vapor that rises into the atmosphere. Plants also contribute through transpiration, releasing water from their leaves into the air. As water vapor accumulates, it cools and condenses to form clouds, floating silently above the Earth's surface. Eventually, clouds release their moisture through precipitation in the form of rain, snow, or hail. Water returns to rivers, lakes, and oceans, ready to begin the journey again. Along the way, water seeps into the ground, replenishing aquifers and nourishing plants and soil. This underground flow is a hidden but vital part of the cycle, sustaining ecosystems even far from surface water. The water cycle also interacts with other natural systems. It shapes mountains and valleys through erosion, influences weather patterns, and moderates temperature across continents. Without this continuous movement, life as we know it could not survive. By observing rivers, clouds, and rainfall, we witness a process that quietly connects every corner of the planet. The water cycle is a reminder that Earth is alive with movement, endlessly renewing itself, and that even the simplest drops of water are part of a complex, interconnected system that sustains all life on our planet. Earth's story spans billions of years, far longer than humans have existed. To make sense of this immense history, scientists use the geological timescale, a system that divides Earth's past into manageable intervals, revealing how our planet has evolved over unimaginable stretches of time. The timescale begins with the Precambrian, a vast period covering nearly 90% of Earth's history. During this time, the planet's crust stabilized, oceans formed, and the earliest life appeared, mostly microscopic organisms floating in ancient seas. Though life was simple, the foundations for all future evolution were being laid. Following the Precambrian, Earth entered the Paleozoic, an era of incredible change. Complex life forms emerged, oceans teemed with diverse creatures, and the first plants began to colonize land. Mountains rose and continents drifted, reshaping the planet's surface. The Mesozoic, often called the Age of Reptiles, saw the rise of dinosaurs and the first birds and mammals. Continents continued their slow drift, oceans shifted, and massive volcanic activity transformed landscapes. Finally, the Cenozoic, our current era, brought the rise of mammals, the shaping of modern continents, and ultimately the appearance of humans. The geological timescale is more than a timeline. It's a lens through which we can understand Earth's processes, climate changes, and the evolution of life. Fossils, rock layers, and radiometric dating all serve as markers, helping scientists reconstruct events that happened millions or even billions of years ago. By studying these intervals, we gain perspective on Earth's immense age, the gradual forces that shape it, and the delicate balance that allows life to thrive. The geological timescale reminds us that our planet is ancient, dynamic, and constantly evolving, a story still unfolding beneath our feet.
Earth holds countless secrets beneath its surface, from hidden mineral deposits to ancient structures, yet scientists don't always need to dig to uncover them. Modern Earth science relies on a remarkable set of tools and techniques that allow researchers to explore the planet remotely and safely. One of the most important methods is seismic imaging, which uses waves from natural earthquakes or controlled sources to map underground structures. These waves travel at different speeds through various materials, revealing hidden layers of rock, magma chambers, and even fault lines. It's like taking a CT scan of the Earth, offering a detailed view without moving a single rock. Satellite technology also plays a crucial role. Orbiting instruments measure subtle changes in Earth's surface, gravity, and magnetic field. These observations help track mountain formation, glacier movement, and shifting tectonic plates. Satellites can even detect underground water, monitor volcanic activity, and observe changes in soil composition across vast regions. Geophysical surveys on the ground add another layer of understanding. Techniques such as magnetometry, electrical resistivity, and ground-penetrating radar allow scientists to identify minerals, cavities, and buried structures without excavation. Combined with careful observation of surface features, these methods create a comprehensive picture of Earth's hidden processes. By studying the planet in this way, scientists uncover Earth's history, predict natural events, and understand the forces shaping its future, all without disturbing delicate ecosystems or landscapes. This invisible exploration demonstrates that even when we cannot touch it, the Earth speaks to those who know how to listen, revealing secrets hidden beneath every layer of rock and soil.